Today we're going to skip over some of the previous exercises, noting that we're going to bypass the Pythagorean identity and I think another exercise. So in your notes, make sure that you're up to solving equations. Okay. All right, so solve the following equations over the stated domains. Now, let's go back to something that you would have done previously. So let's just say that you're going 2x plus 3 equals 5. Now, and a good way to think about that is, when is the graph of y equals 2x plus 3 equal to 5? Or when is the value y going to be equal to 5? So we can do this graphically by going, all right, there's the y-intercept at 3, and our function goes like this. So when is the y value going to be 5? It's going to be somewhere there, okay? Now, graphically would not be a good way to do this, because you guys sort of know that all you do is you subtract 3 from it, which is going to be 2, x is equal to 1. And so when x is equal to 1, probably should do it there, the y value is going to equal 5. It's actually no different for trigonometric solves. So I'll just show you how this will work by pulling up GeoGebra and explaining exactly what we're trying to do when we solve trig functions. So what I'm going to do is sketch cosine x first of all. There it is there. And what I want to know is, when is the function cosine x going to give me a value of a half over the domain 0 to 2 pi? Now, it's really important to note that, because without a domain there, it actually happens very often, okay, or a number of times. I'm going to graph the function y equals a half, and note that the function cosine x equals a half between 0 and 2 pi is going to happen there and there. It happens twice. Without that domain, though, have a look at how many times it happens. It's a half there, 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 it's a half there. So noting that without a domain, this becomes a problem that has infinitely many solutions, because it also happens in a negative direction. Okay, so we get a half there, half there, half, half. So it's really important to check your domain, and that will tell you how many solutions we're actually after. All right, once we know what we're doing, this becomes not too bad a problem to solve, and it can be fairly, what's the word, algorithmic. Okay, so the first thing we do is we think about, when is cosine equal to a half, and we call this our base angle, BA. All right, so what I do is I scribble a unit circle down and I go, all right, I know that cosine is going to be a half for a particular angle in the first quadrant. Okay, now that angle is going to be pi on 3, the cosine of 60. So my base angle is pi on 3. Then what I do is I go, all right, I'm starting at 0, I'm going to be a half there, and I'm going to keep going around, and I wonder when I'm going to be a half again. Well, it's going to happen down here, okay? And that's going to be either side of 0. So if our base angle is pi on 3, right, x is going to be pi on 3. And the next time it's going to happen is all the way around here, or 2 pi take away pi on 3, which is going to be 6 pi on 3 take away pi on 3. That's 5 pi on 3. So they're the two scenarios where we're going to get a value of a half. Now again, graphically, I'll just show you what that looks like. So here is cosine, and it's pi on 2, pi, 3 pi on 2, and 2 pi. So what cosine does, it starts high, down, and then back up again. All right, so this is what cosine looks like. And we're saying, when does it equal a half? So there's a half there. It's going to be there and there. So notice what happens as I move around the unit circle. I get one solution early, which is this one here, and I've got to keep going all the way around until I get, I call this a late solution, okay, down there. So the graph and this unit circle seem to correlate with each other quite nicely. Right, now before we proceed any further, what we'll do is we'll actually ask the calculator to do this solve for us. So we're going to go solve cosine x equals a half for x, all right? Now when I hit enter on that, the calculator gives us this information here. Now what the calculator is basically saying is that there is infinitely many solutions, and that's what this constant idea means, okay? It's saying, I can't give you all of the solutions because it happens infinitely many times. So if you want to actually get a finite number of solutions, you've got to feed the calculator a restricted domain. So what we'll do is we'll find this. We'll say solve cosine x equals a half comma x with x, or let's give it the domain, which is going to be 0. Where is it? Less than or equal to x, less than or equal to, whoops, 2 shift 0, so 2 pi. And there we go, we've got the two solutions then over the restricted domain. So the calculator then has got the kind of area to look, and it goes, okay, over that domain specified, these are the only two solutions, or the only time where cosine is going to equal a half. Okay, so you can check your answers quite easily with a calculator. All right, when is cosine x negative root 3 on 2? All right, so the first thing we want to consider is, well, when are we going to get root 3 on 2 from cosine? We want a first quadrant base angle. And root 3 on 2 is going to be pi on 6. That's the cosine of 30, right? Now what I do is draw my dodgy unit circle and go, all right, when's this going to happen? Or when is cosine negative? So it's going to be over here, okay? This is where we're going to get a negative root 3 on 2. So I know our base angle is pi on 6, but that's a first quadrant angle and cosine's positive. I want negative root 3 on 2, all right? So that's going to happen all the way over here. Now that's pi on 6 less than pi. So that's going to be 6 pi on 6, that's 5 pi on 6. And there is our first solution, is pi on 6. Right, and what's going to happen is we're going to get it again very quickly, okay, which is going to be pi on 6 more than pi. So that's 6 pi on 6 plus pi on 6. So our other solution is going to be 7 pi on 6. All right, again, if we look or think about that graphically, it's important to know how this works. So pi on 2, pi, 3 pi on 2, and 2 pi. All right, we got one negative one, so it's going to go like so. Okay, and negative root 3 on 2 is 1.7 negated, half of 1.7 is roughly 0.9. So let's say it's negative 0.9. Let's look across there. We get one solution and one solution. And you note the quick succession in which the solutions happen graphically. It goes bang and bang. All right, so quick and quick. All right, so again, note that these solutions happen in quick succession. This is actually wrong. I forgot to put 5 pi on 6 there. So 5 pi on 6 and 7 pi on 6. So please make sure that you update that one there, because the cosine of pi on 6 is positive root 3 on 2, not negative root 3 on 2. Okay, again, we can quickly do this on the calculator to make sure, which is going to be shift root 3 with a negative sign, and we get 5 pi on 6 and 7 pi on 6. All right. So sine of x equals negative root 2 on 2. So this one here, it's important to note that 1 on root 2 is equal to times root 2 times root 2, that's equal to root 2 on 2. So this one here, the 1 on root 2 is, I think about that, I know it's a little bit naughty to think in degrees, but I think about that as 45 degrees, or pi on 4. So I'm going to state my base angle in the first quadrant, which is pi on 4. Dodgy unit circle time. Okay, and now what I'm looking at is, when is this going to be negative? All right, so here's the first quadrant version, which will give you that. So what we're going to do is go around, no, still positive, go around, and it's going to be here. All right, so it's going to be pi on 4 more than pi. So that's 4 pi on 4 plus pi on 4. The first time it's going to happen is x is equal to 5 pi on 4. I'm going to keep going, and it's going to happen there, which is pi on 4 less than 2 pi. So that's 8 pi on 4, take away pi on 4, it's 7 pi on 4. Another one, cosine of x is equal to negative a half. So when is cosine a half? That forms our base angle. Our base angle is going to be pi on 3. Cosine of 60 is a half. All right, now what we're going to do is note that cosine is positive there, We want the negative version of that, so it's going to happen over here, which is pi on 3 less than 3 pi on 3. That's going to be 2 pi on 3 as the first instance where it's going to be negative a half. So we're going to get to here, we're going to keep going and then look up. All right, where am I here? I'm pi on 3 more than pi, which is 3 pi on 3 plus pi on 3, or pi on 3. All right, now here's an interesting problem. Okay, so this one here, what we're going to note is that this thing here is a period change. Okay, so what we're doing is dilating the function cosine x by a factor of a half from y. So what happens is we want to get the solutions for negative root 3 on 2. What's going to happen is because we're doing it over a domain of 0 to 2 pi, this is not going to be the standard cosine function. We're actually going to get two lots of the cosine function before 2 pi. Now, why is it important to note that? It's important to note that because, well, or how do I know that? One, I know that the period of this function here is going to be pi, okay, because it's going to be 2 pi on 2, which is pi. So that means that I'm only going to get one version of it from there to there, and then another version. Now, I want to know when it hits negative root 3 on 2. Remember, that's down there somewhere. So it's going to hit once, twice, 3, 4. It's going to get hit 4 times before we get to 2 pi. That tells me what I need to do is generate 4 solutions. There's going to be 4 solutions to this particular problem. All right, so here's the basic method. So we go about it the same way, and we pretend that we're solving for cosine x. So when is it root 3 on 2? The base angle in the first quadrant is going to be pi on 6, 30 degrees. All right, so now what I'm going to do is dodgy unit circle. Pi on 6 will give me the positive version, so it's going to be over here. All right, and that is going to be pi on 6 less than pi, which is going to be 2x equals 5 pi on 6. And then it's going to happen again very quickly after it at 7 pi on 6. So pi on 6 more than 6 pi on 6. All right, so then we come back around here and we're going to generate another lot of solutions. Now I know I've gone 2 pi and then 4 pi, but I'll show you what will happen in a sec. So I'm going to be here at 2 pi. This over here is going to be 3 pi, which is 18 pi on 6. So this one here is going to be 17 pi on 6, because basically it's going to repeat itself every 2 pi. Okay, so what I could do is plus 2 pi to this solution and plus 2 pi to this solution. So 2 pi, remember, is 12 pi on 6, plus another 5 pi on 6 is 17 pi on 6. So we've got 12 pi on 6 plus 7 pi on 6 is 19 pi on 6. Now, I know what I've done there is I've generated out of domain solutions, okay? So to bring the solutions back into the domain, what I'm going to do is dilate each of these solutions by a factor of a half, or if I was solving for x, divide that by 2 and divide all solutions by 2. So that will give us 5 pi on, so 5 pi on 6 divided by 2, we just double the denominator, that's 5 pi on 12, 7 pi on 12, 17 pi on 12, and 19 pi on 12. The calculator will handle this quite well. Okay, so if I chuck the 2 into this, what the calculator will do is go, you're dilating by a factor of half, so over 0 to 2 pi, there's obviously going to be more solutions, and there they all are. All right, so a few more problems to do here. Again, we're going over the domain 0 to 2 pi. We've got a dilation factor half from y, which means that I'm going to get 4 solutions again. So let's solve this. All right, now the way we solve it is when we want to know when this particular trig function is equal to 0. Right, well, let's make it really easy for us. And instead of solving that one when it's equal to 0, we're going to solve it. I'm going to add root 3 to both sides and divide by 2. Now notice how it just so happens that we want to know when cosine 2x is equal to root 3 on 2. We know an exact value for root 3 on 2. This is easy, this one, okay? So what we're going to do is note our base angle in this instance is going to be 30 pi on 6, perhaps unit circle. So there we're going to get a root 3 on 2. And it's going to then go all the way around the circle, the unit circle to this point here. Okay, so this is going to be another one. So we're going to get 2x equals, because this is the one I'm solving. I know originally I'm solving this, but when I transpose it, it's easier to solve this than it is this one here. So we're going to go 2x equals, so I get a pi on 6, and then it's 12 pi on 6, take away pi on 6, which is 11 pi on 6. Now remember, because of this dilation factor from y, what I've got to do is generate 4 lots of solutions. So I'm going to generate another one. So that's going to be 7 pi on, no it's not, it's going to be 12 pi on 6 plus pi on 6, which is 13 pi on 6. Basically, I'm doing the same thing I did before, which is add 2 pi to this solution and add 2 pi to this solution, because again, I hit it once, and when's it going to be there again? It's in another 2 pi, 4 pi, 6 pi, etc., etc. So 13 pi on 6 is there. This is going to be 24 pi on 6. Take away 2 pi is 23 pi on 6, or adding 12 pi on 6 to 11 pi on 6 is 23 pi on 6. X is equal to pi on 12, 11 pi on 12, 13 pi on 12, and 23 pi on 12 once I've done the dilation. And this pulls, what it does is it pulls all the solutions for the standard 2 pi period back into the domain for this particular period of cosine. Okay, another one. So can't solve, well, I could solve this one, but it's much easier to reprocess it. Sine of x equals root 3 on 2. What's our base angle? So when is sine equal to root 3 on 2? It's going to happen at, that's going to be 60 pi on 3. Okay, so pi on 3 is when it first happens. So we're going to go x is equal to pi on 3. When's it going to happen again after that? Very quickly, in fact, at 2 pi on 3. All right, because there's no period change on here, these are the appropriate solutions. Okay, and again, let's see why graphically that's the case. Pi, 3 pi on 2, and 2 pi, this is sine. So what it will do is go like that, for that being 1. Now root 3 on 2 is roughly 0.9. So there we go, bang, bang, 2 quick solutions. And then over the domain of 2 pi, never again. So we get our first 2 solutions very quickly, and then we'll never get root 3 on 2 for the rest of the journey around the unit circle. All right, so sine 2 sine 3x plus that. So again, what we'll do is we process that into -1 on 2. All right, now what this is this is a dilation 1/3. Okay, so what this will actually do to sine x is actually over the period of 2 pi, it's going to have 1, 2, 3 repetitions of that. Okay, so 1/3 will mean 3 repetitions of the sine function from 0 to 2 pi. Quarter, or if that's a 4, then we'll get 4 repetitions, 5 repetitions of it over 0 to 2 pi, because that'll be dilation 1/5. Okay, all right, let's get started on this one here. So we'll grab our base angle. When is sine a half? That's going to be 30, or pi on 6. All right, now what we're after is -1/2. So if that's our base angle there at pi on 6, it's going to happen over here at 5 pi on 6. Wrong way, there. And it will also, no, okay, let's undo this. So good to see you, or have you see me making mistakes. I can't even say the word mistake. All right, what we're trying to do is make it equal -1/2. So our base angle is pi on 6. That's positive. When's it going to be negative? Start going around all the way down here will give me the first negative. So that's going to be 6 pi on 6 plus pi on 6, 7 pi on 6. Then keep going around, and that's going to be 11 pi on 6. So 12 pi on 6, take away pi on 6. Let's start getting our solutions. So we've got 7 pi on 6, 11 pi on 6. All right, and then what I can do is simply add 2 pi to both of these solutions to get the next ones. I don't have to reconstruct it by going around the unit circle. So 2 pi on 6 is, with this denominator, 2 pi is going to be 12 pi on 6. So this is going to be 19 pi on 6. So 2 pi plus 7 pi on 6. This is going to be 23 pi on 6. Now let's add another 12 to that, which is going to be 29, 31 pi on 6. And 33, 35 pi on 6. All right, so some shocking outer domain solutions, but what we'll do is dilate them all by a factor of 1/3 from the y-axis. So let's divide them all by 3, 7 pi on 18, 11 pi on 18, 23 pi on 18, 31 pi on 18, and 35 pi on 18, which brings all of the solutions back into the domain. Okay, to operate on tan, it's really no different. Okay, so what we want to know is when the tan of x is equal to negative root 3. So a base angle, so when is tan root 3? That's going to be when tan is at pi on 3. So a base angle is pi on 3. All right, so it's going to happen here in the first quadrant. That means that at 2 pi on 3, it's going to be the negative version of it. Okay, so x is going to be pi on 3, and then we're going to have to wait until we get to this point here. Now notice that this time around, what we're going to do is plus pi to tan because that's the period of tan. So we're going to plus pi, and then we get to this point here. So that's at 4 pi on 3. I've made that mistake again with the base angle. That one should be 2 pi on 3 because that gives us the negative version. And then it's not 4 pi on 3. This one here is 5 pi on 3. Okay, again, could chop that mistake out, but it's important that you see me making mistakes. You'd see me doing this in the classroom as well. So that's no dramas. So 2 pi on 3 plus 3 pi on 3 is 5 pi on 3, which is our next solution. Okay, so our final one of the day will be this one here. So this is tan 3x equals 1 on root 3. That's the one that we're going to attempt to solve. So 1 on root 3 is a base angle of pi on 6. So we want to know when tan is equal to pi on 6. Okay, so it's going to be there and there. Okay, so we're going to go 3x equals, so pi on 6, and then it's going to be 6 pi on 6 plus another pi on 6 is 7 pi on 6. Now they're the solutions between 0 and 2 pi, but note that we've got this dilation factor of 3. All right, so what that's going to do is it's going to generate many more solutions. Okay. So what we're going to do is start to add pi, and instead of what we want to do is go round once, twice, 3 times. So we're going to generate 6 solutions here. So pi on 6, and then we're adding pi to this solution, which is 6 pi on 6, and we're adding 6 pi on 6 to this solution as well. So that's going to be 7 pi on 6. So interesting how that happened, okay, because notice that I generate it here. Okay, so I'm going to generate exactly the same solution by adding pi to this one here. We're going to get 7 pi on 6, then it's going to be 13 pi on 6, then it's going to be 19 pi on 6, then it's going to be 25 pi on 6, all right, and then it's going to be 31 pi on 6. So we've got 1, 2, 3, 4, 5, 6. All right, now what we're going to do is bring all of these solutions back into the domain by dilating them. Pi on 18, 7 pi on 18, 13 pi on 18, 19 pi on 18, 25 pi on 18, and 31 pi on 18. Right, so there's all of our solutions, okay, for that. All right, so the exercise now will be to do all of these questions, okay, so noting that these ones here by hand, 2 and 8 with Kaz, do exercise 14L, okay, question 3, and go back to 14J and do these particular sketches here, noting that now what I'm going to get you to do is graph with the x